In this video, we'll discuss about bifurcation. We have seen that in Van der Pol oscillator, depending on the values of mu, the nature of the fixed point changes. We have seen stable fixed points, unstable fixed point, even limit cycles, depending on the values of mu. This kind of sudden changes in the dynamics because of the change in the values of the parameters is called as bifurcation. The value of the parameter at which this change occurs is called the bifurcation value. We now discuss some simple examples of bifurcations in one dimension. Let us look at this dynamical equation x dot equal to mu minus x square. Here f of x equal to mu minus x square. Therefore, the fixed points are given by equating it f of x to 0. So, we get x equal to plus or minus square root of mu. Here f prime of x is minus 2x. So let's look at the nature of the fixed point depending on the values of mu. For mu is equal to 0, the fixed point is x equal to 0, f prime of 0 equal to 0. So it is neither positive nor negative. So the method of linearization fails here. But from the dynamical equation x dot equal to minus x square for mu is equal to 0, this f prime of x turns out to be negative for x equal to 0 and positive for x less than 0. Therefore, this x equal to 0 fixed point is half stable. For mu greater than 0, the fixed points x plus or minus square root of mu, f prime of at x equal to square root of mu, f prime becomes minus 2 mu, minus 2 square root of mu. This fixed point, so this is negative, so this fixed point becomes stable. For x equal to minus square root of mu, f prime becomes positive. It is equal to 2 square root of mu. Therefore, this fixed point is unstable. For mu less than 0, there are no real fixed points. So, as mu increases from negative to positive, a fixed point suddenly appears at x equal to 0 and this fixed point is half stable. And with the increase of mu, this half stable fixed point bifurcates into one stable and one unstable fixed point. This type of bifurcation is known as saddle node bifurcation. So we can see the picture here. Let's take another dynamical equation. So we take x dot equal to mu x minus x square. In this case, the fixed points are x equal to 0 and x equal to mu. So f prime of x is calculated as mu minus 2x. For mu is equal to 0, the fixed point x equal to 0 gives f prime of 0 as 0. So the method of linearization fails here. But the dynamical equation x dot equal to minus x square, from this we can observe that f prime of x becomes negative for x greater than 0 and it becomes positive for x less than 0. So therefore x equal to 0 is half stable. For mu less than 0, there is a fixed point at x equal to 0. Here at f prime of 0 becomes mu. So mu is negative. So therefore x equal to 0 is stable fixed point. At x equal to mu, f prime becomes minus mu. But mu is less than 0. So f prime becomes positive. So x equal to mu is unstable fixed point. Let's look at the case for mu greater than 0. Here we have the two fixed points x equal to 0 and x equal to mu. For the case of x equal to 0, f prime becomes mu, but mu is positive, so this is f prime is positive. So x equal to 0 is unstable fixed point. For x equal to mu, f prime becomes minus mu. Since mu is greater than 0, f prime becomes negative. So x equal to mu is stable fixed point. In this case, bifurcation value at x equal to 0 exactly similar to the saddle node bifurcation. But as you go from negative to positive, here the stability of the fixed points at x equal to 0 and x equal to mu gets interchanged at the bifurcation value. So this type of bifurcation is known as transcritical bifurcation. Here fixed points do not disappear at the bifurcation point, which we have seen in the earlier saddle node bifurcation case. Here just change their stability. So let's look at another dynamical equation. Here we have x dot equal to mu x minus x cube. So the fixed points, by equating the right hand side to 0, we get x equal to 0 and plus or minus square root of mu. For f prime of x is mu minus 3x square. For mu is equal to 0, so there is a fixed point at x equal to 0, but f prime 0 is again 0. Method of linearization fails. But from the dynamical equation, x dot equal to minus x cube and f prime of x equal to minus 3x square. For all the values of x, f prime is positive. So we call x equal to 0 is a stable fixed point. For mu greater than 0, there exists an unstable fixed point because f prime is mu and it is greater than 0. And for the case of plus or minus square root of mu, we get f prime as minus 2 mu, right? Since mu is greater than 0, this is stable fixed points. So for mu less than 0 case, we have only one fixed point x equal to 0, but it is f prime is mu, and but mu is negative, so x equal to 0 is also stable fixed points. So in the picture we can see in the picture how this bifurcation works in the pictorial point of view. So this kind of bifurcation, we clearly call it as pitchfork bifurcation. It looks like a pitchfork, but this kind of behavior is called as supercritical pitchfork bifurcation. Let's change the sign in the same dynamical equation and see how the bifurcation changes. So now we have x dot equal to mu x plus x cube. So f prime becomes mu plus 3x square. For the case of mu is equal to 0, we have the fixed point at x equal to 0, but f prime becomes 0 here. Again the method of linearization fails. But from the dynamical equation, x dot equal to x cube and f prime x equal to 3x square, for any values of x, f prime is positive. So x equal to 0 is unstable fixed point. For mu less than 0, there exists a fixed point at x equal to 0 because f prime is mu and mu is less than 0, f prime becomes negative. But for the case of x plus or minus square root of mu, f prime becomes minus 2 mu. Since mu is negative, f prime becomes positive. So x plus or minus square root of mu is stable, unstable fixed points. Not stable, sorry. It's unstable fixed points. For mu greater than 0, we have unstable fixed point at x equal to 0 because f prime gives mu. Mu is greater than 0, it is positive. So this type of bifurcation is called subcritical pitchfork bifurcation. In the pictorial point, it looks like this. Thank you.